Hi, welcome to the Calculus 2 lecture series. And we are in the unit number 2, talk about the different techniques of integrations. So for this lecture is lecture number 10. We talk about the strategy for integration. So basically, this lecture is kind of wrap up most of the techniques we need in the technical integrations. And for each technique, we have separate lectures. And so now, when you're dealing with integration problems, sometimes they're not going to tell you what method to use, right? So what will be the strategy you use when you see problems here? Okay, so basically it's kind of summary lectures for all the previous techniques we learned. Okay, so now let's go to the lecture note here. Okay, so for this lecture note, first I can provide you a table, and this table have the most useful and most frequently used integration formulas. And so if you can, most like, you should be able to, take at least the majority of your integration problems. And so I expect, you should remember all the formulas, maybe till the number 14. Those are the very, very basic. And then if you can remember the another 4, that'd be pretty good. So at least when you try to do it, you will be fast, and so you'll be able to solve it. Okay, so now those are just a summary of the formulas for your reference. Okay, so like we talk about here, this is a kind of like a wrap up lecture. So what are the strategies for here? So I'm going to write a few things, right? So those are the basic strategy we use here. So first things here, I'm going to divide this will be like 3 columns here. So this is what is the methods here. And then this is, I'm going to provide a simple example, just demonstrate what I mean. And so what is the first step? What is this methods we talk about? So that's why I call it first steps here. Okay, so the first methods here. So the method number 1. All right, so we want to, so this is a common ones here. You want to rewrite the integrand. Okay, so that will be the first methods here. So you take a look at what is your integration, and you might want to rewrite it. So they have several ways you can rewrite it. So this is where our example comes in, right? So you can rewrite it in the UCO algebra. Okay, it's just a combined term, the FOIL terms, and use your algebra skill to see you'll be able to rewrite it into a form you can take the integration. So for examples here, this is what we, for example, if you have x squared, and this is 1 plus 2 square roots of x here, dx. So for this integrations here, so when I mean the rewrite, so basically you can just FOIL it, right? So, or you can just like take the, the break out the parentheses. So if you rewrite this one to like x squared and the plus, and here is your constants, right? So 2, then this is x squared, this is x to the negative 1/2. So this is x to the what? 3/2 dx. So after you rewrite it, then it become, like it become like similar like to the polynomial. This, of course, this is not like the x to the 3/2, but you can use the power rule and try to take the integration. So after you rewrite it, then this integration will be pretty simple, right? So this is the first way, you see it, then you see maybe you can rewrite it into a way you can apply the simple integration rule, like the power rule, exponential, those things. Then the next things here, this is what we talked before. is we said use the trigonometry identity. Okay, so or we said that this is we call it what? It's a trig integrations, right? So we talk about this, for example, this is what we talk about. This is like a sine, you have a 3x, and let's say here cosine square x dx, right? So we use a different trig identity like the double angle, half angle, and the trigs, Pythagorean identity in the trigs, right? So for here, so we talk about the different combination of sine, cosine, tangent, secant, tangent. So if you see this, you can say, okay, let's see the trig identities here. So now, you can start to do like this, right? So now you can sine, so you can say that this is a sine x square cosine x square, and then because the sine here is a cube, you have a sine x dx, right? So now you see here you have a sine x dx. So you can do a u sub afterward. So this is become the problems we're dealing with before. Then here you will have a sine square. So what is 1 minus cosine square x cosine square x sine x dx, right? So then you can use u sub, and then that will help you. So u sub will be the cosine x, then the du will give you this number. So this is a trig identity. Oh, we call this a trigonometry integrals. We spend I think we talked about it in our previous lectures, this ones, right? Then the next things here, this is what we say, rewrite your integrand, you change your integrands here. Then the other ones here, this is we just covered from the previous lecture, we call this the partial fraction. Right, so for the partial fraction, basically it is dealing with what? The rational functions, right? So for example, we said a partial fraction, if you have something you integrate like this, right? So the x plus 2, let's say the x minus 3 dx. So what is the partial fraction? That means you divide, you separate this, right? So you separate it into a rational function, you'll be able to do what? You'll be able to integrate. So these ones here, after you break down, so you will have, this is x plus 2 negative 1 dx, and plus, okay, you can put like this, so then plus x minus 3 to the 1 dx, right? Use what we learned from the previous, from the previous lectures about the partial fraction. So you see here, these 3 always rewrite. So those are basic idea. You can use your algebra, or you can use your trig identity, or use the partial fractions, to rewrite it. All right. Like I said, there probably some other method, but those are the 3 we use most frequently. Okay, so now the second strategy is here, we can do we talk about is the substitution. Okay, so the substitutions here. Okay, so the first ones here we talk about, we call this a direct substitution. And most of the people call this is u sub. All right. So, for example, here, if I have something like here, so the x square, right? So this is x cube plus 1 to the dx. So the key things here is kind of like a spy. You recognize, if you let a certain number become u, and then what happens? So the remaining part has to be the du's, right? So like for here, you said that u is equal to the x cube plus 1 here, right? Then you can have a du is 3x squared dx here. So that's why, for the u sub, typical, if you kind of see, especially for the rational function, if the one the degrees is less than other one, then U sub probably will be a very good substitution methods to use here. All right, so it's kind of like play the detectives here. All right, so then the next one we talk about is the trig substitution. All right, so it's a trigonometry substitution. And this is the one we also spend the one whole lecture to talk about. This is the one is still dealing with the, if you remember, it's the square roots of the things, right? So for example, this is x squared, and this is 4 minus x squared, right? So then we have a squared minus b squared, a squared minus x squared, x squared minus a squared, x squared plus a squared in the square roots. All these are good for the what? Good for the trigonometry substitution. So you should be very familiar if you see this is the square roots, right? So immediately you know x here, I'm going to be 2 sine theta here. Right, and then we know the dx is going to be 2 cosine theta d theta. Then remember, you need to use a little triangle to do that, and we did many examples for that. Okay, so then the next thing here, the substitutions here is we call this a rationalize. And the rationalize the substitution, remember the rationalize the substitution, the key idea is to get rid of the roots functions. So then change the function become what? Become a rational function, become like the rational function with a polynomial on the top and the polynomial on the bottoms, right? So like for example, this is the examples here. We have this is x, and I have the square roots of the x plus 1 dx here. So for this type of the functions here, I have the square roots here. So we want to rationalize it. We don't want the root function. Root function in general is difficult to dealing with. So you will say u is the square roots of the x, right? And then you will say u squared is x, and then you take the derivative, both sides 2u du is equal to dx, then you substitute back. So remember we did it in the previous lecture. If you have different roots, right? So one is the cube roots, one is the square roots, then what you need to do, now your u need to find this common. If you have the square root is 2, and then if you have cube root is 3, then you will do like u is equal to the x to the 1/6, right? So you want to find the least common multiplier and then put it into the roots here. So in that way, you can get rid of the roots, right? Okay, so this is what the second things we talk about. So you want to do the substitutions here, all right? Then the last things, if none of these strategies work here, then the last things here you want to do, well, not the last things. So another strategy is, this is the one we call this the integration by parts. So this one is the integration by parts. And so for example, we talk about in here, this is x cubed, and then this is the natural log x dx. It really doesn't match any of the strategy we talk about here. Then the whole thing here is you want to change that. So you hear the integration by part is, we said here is u is equal to the natural log x. Then all the remaining here, we will say is the dv's, right? Then we said, then this one you take the derivative, so this is a du is 1 over x dx, and this you take the integration, so this is x force is equal to v. Then if you remember, then we say this is uv minus what? So this would be uv minus vdus, right? That's how do we do the integration by parts. In fact, integration by part is very, very commonly used here. All right, so those are the strategy. Okay, the worst come to the worst if none of them work, right? So other things you can do is you can use the integration table. Okay, so the integration table, at the back of the textbook, they have the integration table. So basically, some very complicated or difficult integration, somebody already did for us. And then you just go to take a look, to see your integration form match any of the form in the table, right? Then you'll be able to use the integration table and find the integrations here. So that will be our last one. So if you really run out of the options here, you don't know how to do that, and then you probably go check to see the integration table. Is there any chance the problem you try to solve match one of the form people already derived the formula for you? All right, so basically those are the strategies, and those are the things we went through since we started the integrations here. All right. Okay, so now here, this is the fun part. That's why for the integration is really have more fun than the derivative, because derivative, I always say, doesn't matter how complicated your function is. If you are patient enough, you can get the answer. If your algebra is good enough, you can get the answer, right? So you just apply the product rule, quotient rule, chain rule, and so it will get there, right? Maybe it's very complicated form, but you'll get there. But integration is a different story, right? So sometimes it's a kind of a challenge to work on that, right? So it's not necessary. It's always you'll be able to get the solution right away here. Okay, so now let's see here. So here, this is the first problem here. This is the EX over EX minus 1. So in here, I'll say, what I need to do is here. But I do know the EX has a good character, right? Because EX derivative is itself. So also this fraction gave me trouble. So I said, okay, maybe I will do a U sub here, right? So I will say U is equal to the EX minus 1, right? So if U to the EX minus 1, so the du, EX derivative itself is the EX dx here. That's good. So because the remaining term of this integration is EX dx, I got them all covered. So now I can rewrite this into what is U. So what is this green one? The green one is EX dx, right? So it's equal to du here. So wow, I simplify that. And we all know what is the 1 over U, the integration is natural log U, right? Plus C. And don't forget, we always need to replace back. So here, this will be the EX minus 1 plus C here. And you might ask me, said, how do you know? You said U is equal to the EX. I said, most likely when you did enough problems, sometimes it's kind of just you can spot it, right? Of course, sometimes after you try it, you say it doesn't work, and then try different methods here. Okay, so the part B here. The part B, this one is really, I said, okay, part B, what method I need to use? As soon as I spot this square root with a squared plus x squared, then I immediately know I can use what? The trig substitutions, right? So what is this for? That means my A is equal to 2. So I can use the trig substitutions for the, for the square roots of the a squared plus x squared. So if you remember what is the trig substitution, I would say x is equal to what? 2 tangent theta, right? So 2 tangent theta. And then just follow the same things. And then you say dx is equal to the 2 secant square theta, d theta. Then you divide the 2 both sides. This is the tangent theta. And do you remember that's what we did? So now you draw a little triangle. So the trig substitution is very, very much the same routine. As long as you you find out what is your substitutions, right? That is what is count. So this is the theta. So this is x over 2, right? So what is here? So Pythagorean theorem is 4 plus x squares. All right, so 4 plus x squared, and then because we know tangent and the secant, they are partners, right? So they are we call this the partner of the primes. So I'm going to find the secants here, right? So the secant theta here, based on this triangle, will be the hypotenuse 4 plus x squared over what? Over 2. So now I can send this one. This is 2 secant theta equal to the 4 plus x squared. So now let's try to substitute these ones here to see if we can simplify that. Okay, square roots of 4 plus x squared, so it's a 2 secant theta. Okay, x cubed. Okay, x is, so what is x cubed here? X is 2 tangent, so this is 2 tangent theta to the cube, right? Wow, dx and times 2 secant square theta d theta here, right? Okay, so now let's take a look. We can simplify anything here. Okay, this 2 and the 2 you can cancel. Second, I can cancel a second. So now this integration will just be what? 8. Then what is here is tangent to the what? Tangent to the third theta and second theta d theta. When you see here, now you say, oh, okay, this is a tangent secant combinations, right? So what? So you say, okay, this is the tangent secant combinations here. So what I can do here, remember both of them are, so I can do what? I can take out 1. So this will be the tangent square theta. Then I will have the tangent theta, right? Tangent theta, secant theta, d theta here. Now I know this one just you you see that, and then you know this is the derivative of the secant. So I need to change the secant. So this one is here. What is the tangent square? Tangent square will be secant square. So will be tangent square will be secant square minus 1, right? So this will be the secant square, right? So this will be the secant square theta minus 1. Then I have a tangent theta, secant theta, d theta, right? So here, right? So the tangent square, I use the identities here. So this problem involves several of the strategies here. Now in here you will have 8. And what is the first integration? The first integration will be the second what? Secant square theta. Then you have a tangent theta and the secant theta, d theta. Then minus here tangent theta, secant theta, d theta here, right? So this one is easy. This one I know that this is the what is the integration for this one? This is the secant theta, because the secant theta derivative is tangent to the secants, right? So for this ones here, so you have a secant square and then the secant theta. So what you need to do is here, you need to use u sub. So you will say u is equal to the secant theta. Then the du is equal to the secant tangent theta and the secant theta and the d theta. So this one will become the u squares, right? So this integration will become the u squared du, right? So now everything, so I will skip a few steps. So here, now this one is a u cube over 3, right? So what is the, so what is the u cube? U cube, so it's u cube over 3. So u is the secant cube theta over 3 and minus what? Minus this one here will be So what is the, this one will be here, this one will be the, so we say this is the second theta, right? Okay, so after you do that, plus C, and, but my, what is my, you know, the, what is my final answer has to be in the X, because my original problem is X. So now you have A times, second is here, right? So second is 2 of the 4 plus X here. So you will have 3 times 2 over, so this is the 8, and this is 4 plus X squared to the what? 3/2. Then minus here is 2, and this is the 4 plus X squared plus C, right? So then if you want, you can carry out and simplify it. Right, so this problem is really involved several. First, you need to use the trig substitution. This, after you use trig substitution, it will become the trig integral. So you use trig identity. After you do the trig identity, then you need to use U sub, right? So it's kind of like involves 3 different methods here. All right, so let's take a look at these ones here. This is EX minus 1. And the EX dx is here. So for these ones here, first things you can say, hey, just follow like what we did the other one. I can say U is equal to the EX minus 1. And then I will do a du is equal to EX dx. The problems here, this EX is in the denominator. So you know you cannot, you know, set this one. So for here, you can, you know, there are sometimes not very unique ways. Here, let me show you what I will do here, right? So the U, the EX minus 1, I will use, I want to demonstrate another, you know, the strategy we talk about. So EX minus 1, this one really, I can separate that out. Right, so it's a common denominators, right? So I can just break this into the EX. Then here, this will be what? This is 1 minus 1 over EX dx, right? So you can rewrite it into algebraically. And then in here, this is the 1 minus the e to the negative x dx. Now the integration is pretty easy. So what is here? This is EX minus negative e to the negative x, right? Plus what? Plus c. So remember, we talked about the integration. We said e to the ax dx, right? Then this one will be a to the e to the ax plus c. Of course, you can prove this by using the substitution, but now if you remember that, so for these ones here is a is -1, so that's why you have -1s here, right? Okay, so now you will have x plus the e to the negative x plus c. Right, so for this problem, that's the, you know, that would be the, you know, be pretty, you know, the easy ones to do that, right? Okay, so that if you do the algebra part to rewrite your integrations here. Okay, now let's take a look at the part D's here. Part D, I have a 2x plus 1 x squared times x plus 1. This one looks like what? This one looks like a rational function. Right, so have a polynomial on the top and have a polynomial on the bottom. Then the bottom also is pretty nice. They already have the, you know, the multiplier of the, you know, the terms there. So probably this will be a very, you know, the easy to do by using the partial what? Partial fractions, right? Okay, so you can rewrite these ones here, 2x plus 1, x squared, x plus 1. You can rewrite into Okay, so remember, right? So here, this is the x to the what? X to the squares, right? So when you rewrite partial fraction, what you need to do, so here is x, then you need to continue increase the power, right? This is x squared. Then the last one is linear, so it's x plus 1. Then you add these threes, right? Then what do you have here? You put a constant. Because this is linear, so you say A, B, C. Right, so now remember what we did here. You need to solve the, so you need to solve the ABCs, right? So we say we go back here, we will do this one here is x squared, x plus 1. Now, what is the A going to be? A going to have x and x plus 1. Then B is equal to the x plus 1. Then C is equal to the x squared. Right? Okay, so now you're going to have 3 variables and 3 equations. And I'm not going to redo the algebra. I just want to show you after you solve it, then the A is equal to 1, B is equal to 1, and the C is equal to -1, right? So this is very, very standard partial fractions. Okay, so now I can rewrite this one will be A is 1, so it's 1 over x plus B is 1, so it's over 1 of x squared, minus C is C is -1, so it's minus x plus 1 dx. All right, so this one is a super easy integration. Also 1 over x. What is 1 over x? Natural log of x. So what is 1 over x squared? This is a power rule, right? So this is x to the what? -2. So you use the power rule, so it will be what? Will be the -1 x to the -1, right? What is this ones here? This is natural log. So this is natural log x plus 1 plus c here, right? So you can rewrite it. If you like, you can combine, if you like, so you don't have to combine these 2 terms. Then this one would be natural log x plus 1, right? By using the natural log rule, and this is over 1 minus x plus c. All right. All right, so let's take a look at the next ones here. Tangent x and the secant x. Immediately I see this is a tangent and the secant combination. So I know this is the trig integrals here. I need to use the trig identities here, right? So I have a secant to the 4. So we love the secant has even power, right? So here, so you immediately know you will have a tangent cube. Then you will have the secant square x, the secant square x dx. The reason why you want to separate out this secant square x, because I know the secant square x is the derivative of the tangent. So then also secant square have an excellent relation with the tangent, right? So I would say this is the tangent, the cube x, secant is the what? Secant is a tangent square x plus 1, and the secant square x dx. Right now, I can use u sub. So if I use u is equal to the tangent x. See here, the du will give you the secant square dx. Here, right? So that's why we say we love to see the secant has even power. That is pretty, so make the substitution, the identity is a lot easier. So this is a tangent. So this one is a tangent 5th power x plus tangent cube x here, right? So it's a tangent x here. Okay, so now let's do the substitution. So this one will be u to the 5th plus u to the what? U to the 3rd. So what is here is du's, right? It's become very, very basic and fundamental. So what is here? So you use a power rule. So this is 6, u to the 6th plus u4 to the 4 plus c. What is the next step? Replace back to the x, right? So this will be 6 tangent x to the 6th power plus 4 is the tangent force to the x and the plus c here, right? So it's very easy, especially when you see those combination like tangent, secant, sine, cosine. Most likely you're going to use the trig integrals. That means you need to use identities here. Okay, let's take a look at the last one. See here, the last one is x to the secant square. The secant square. I know the tangent, the secant square is the derivative for the tangent, but now my problem is here. I have x here. X has really nothing with my trig function, but I have trig functions here. It looks like my strategy for all the other strategy like trig integration, trig substitution, U sub, rationalize sub doesn't work. So let's see here. Maybe I can do substitution, integrate by parts. Remember the integrated by parts, right? So the formula for the integrator by part is like if you have a UdV, you want to change to the UV minus the VDU here, right? This is my integration by parts formula. And when we talk about that, we said that the key things here is you want to separate, you want to break out your integrands here. The one you want to set to be a dV is the one you can integrate easily. All right, so for here, then the u is the one you want to be able to take the derivative easily. So in here, I can set u is equal to x. Right now, all the remaining, so this is the secant square x dx. All the remaining is dv. So one set, you take the derivative. So this one, you will say du is equal to dx. And this one is such a nice form because the secant square, I know is the derivative of a tangent. So if I go backward to take the integration, so what is going to be here? This is going to be tangent x equal to v, right? You integrate. So this is the integrate. And this side is derivatives, right? So that's what we talk about integration by part. Okay, so now this one's here going to be UV. So let me color code that. UV, UV. All right, so this part will be x tangent x minus, right? Minus V. V is here, minus VDUs here. So minus the V, so it's a tangent x and du's, right? Tangent x du is dx. So do you remember? So this is x tangent x. During the, the trig integrals, we derived what is the tangent integrations. Everybody still remember? The tangent integration is the natural log secant x, right? And so plus c. Of course, if you don't remember this formula, then you can rewrite here. So you can rewrite the tangent x is equal to the sine x, cosine x, dx, and x, right? And then you can use the u sub. Then you will say this is u's, right? So this is u, and then the du is sine x dx, and then you will get the same answers here. We did that in our previous lecture. So if you don't remember, the integrated by part, is always good to, go back to review. Okay, so like this is the, we wrap up the most of the integration formula we need to know. I think the challenge is here is just to spot which one to use, right? So some easy one to spot is if you see a special like square root a squared plus x squared, or x squared minus a squared, x squared plus a squared, then you know it's a trig substitution. And the most likely, if you see a rational function, probably is by the integrated by parts, right? If you see a sine cosine combination, tangent secant combination, probably you do the trigonometry integral. So you use identities here. All right. So that's it. So like the integrate by part, if you run out all the other options, then maybe you can try to the integrate by part to see you will be able to, the separate your integration to something easier to integrate. All right, that's it. That's very excited. We learned a lot of the trig formulas, the integration formulas. That's pretty neat, right? All right, that's it. And nice talk to you. And I hope you enjoyed the integration and be able to use all these formulas here. Okay, talk to you later and have a good day. All right, bye.